Hello there. My name is Alex. I'm a PhD student of the IAS1 at the Forschungszentrum Jülich, and I am going to talk to you about forces and relaxations in the FLAPW method, or calculating forces and what we can use them for in FLEUR. And first, I want to be clear with you on all the definitions. When we talk about forces, we talk about the force acting on each atom. So, of the negative derivative of the total energy with respect to the atomic positions. And when you think about the most basic principles of quantum dynamics, you would say, okay, this should be very easy. We can just differentiate the total energy by the parameter, which is the atomic position tau alpha. And according to the Hellman-Feynman theorem, this will just give us the expectation value of the differentiated Hamiltonian. However, this is highly non-trivial to calculate in the FLAPW basis, because we have an explicit dependence on the atomic position in the basis, and the basis is not complete due to cutoffs in the L channels and the G channels for muffin tins and interstitial respectively. The implementation we use in the FLEUR code is based on the work of Yu and his colleagues. It took quite a long time to develop a rigorous definition and calculation method for forces in DFT, especially FLAPW, and they did it in the early 90s and acknowledged the importance of non-standard Hellman-Feynman terms, which I'm going to talk about. And the contributions that you will find in our code and which are written to the output are based on the formulae in their paper. So we're now going to talk about the calculation of forces. I'm not going to talk about each formula explicitly because they get very lengthy, but I'm going to highlight the basic concepts we need. The general concept is we mostly look at integral contributions, volume integrals over an integrand over the whole muffin tin, over the whole unit cell, not only the muffin tin. This then separates into two contributions, the differentiation of the integrand in the muffin tin and in the interstitial region, which you can see right here. And I wrote here that this is only an approximation. Why, I'm going to tell you later, but this is for now what we're going to talk about. And another important factor that goes into the calculation of forces are Pooli contributions. Those are contributions that stem from the explicit dependency of the basis on the atomic positions, which goes as a derivative into the formula right here, and on the incompleteness of the basis set. So there are functions that we will not be able to replicate with our basis, and this needs to be accounted for. The force contributions we have programmed into the FLEUR code are named, as I already said, after the equations in the paper, except for the last one, which combines two of them into a Pooli contribution. And the contributions that I want to highlight are the A3 contribution. This is the actual Hellman-Feynman force, which stems from the differentiation of the Coulomb energy integral for the valence density and the ionic term. The rest goes into equation A4, namely the core electron density. And the other three contributions contain various Pooli terms, whose origin I have just highlighted. However, with respect to the paper of Yu and his colleagues, there are additional force terms that can be taken into account. Dr. Aran Klüppelberg has investigated this in the bounds of his PhD thesis a few years ago. And he did this to reduce the so-called drift force on each system, which is a net force that equals out to not quite zero when you sum all the atomic forces up, which violates the acoustic sum rule and therefore gives you problems, for example, when calculating phonon spectra. And he implemented three corrections to this, which he dubbed the force levels. And two of them contain surface terms, which give you a difference between the correct force on atom alpha and just the integrands over muffin tins and interstitial region, because you need to take into account that you also kind of differentiate the integral borders. And this is accounted for when you explicitly write this surface integral term with the muffin tin and interstitial quantity subtracted from each other. Also, of course, when you take a film system, you will have to think about such volume integrals over the vacuum region as well. I omitted these for now because I don't want to get the formula too lengthy, and it's basically the same concept for these as this is for those volume integrals. Okay, so what are those force levels that Dr. Klüppelberg talked about? There is first an interstitial and muffin tin addition to formula A4, which accounts for additional Pooli terms of the core states. Of course, in a normal framing, the core states are not dependent on the basis, but only on the position, and this is not a problem because they are confined to the muffin tin. But in the FLEUR code, we explicitly allow them to leak into the interstitial, which is managed by the C-tail switch. And if we have this switch on, we also need to take into account that these core tails are giving us additional Pooli terms. This is the so-called force level 1 and contained into equation 20 by a reference paper by Dr. Klüppelberg. The second level goes as an addition to a modification to equation A12 and gives us surface contributions from the kinetic energy operator and the eigenenergies. This is equation 22 in his paper. And remaining surface corrections, which we all get from the same integral I showed you before, are going into force level 3, which is governed by equation 14. As a little caveat, you should only add these force levels if you see that your system has drift forces which need to be eliminated, else it might be too much effort for too little effect. And the level 1 I discussed, the core tails, might extend in a normal calculation to the vacuum, but the force corrections are not considered up to this limit. So they only exist for bulk calculations or for film calculations up to the vacuum border. So this is not completely programmed in that context. And the force levels are only explicitly tested for LDA functionals, or let's say constructed for LDA functionals. If you want to do GGA calculations, there might be some additional terms that need to be taken into account as well, due to the derivatives of gradients in the XZ potential. So now I'm going to talk about the input switches that you need to do force calculations in FLEUR. I highlight here exactly what you will get if you just set up a normal imp.xml file by default. Except for these red switches, they always have to be programmed in or set in manually if you want to use them. You can switch on and off force and relaxation calculations with the LF switch, F or T. You can set the force level to 1 to 3. From 0 to 3, I mean. You can set the force mixing, so how much of the old force you want to keep in each iteration. This is by default 1, so you only take the new force that is calculated. You can set the mixing key to BFGS or to straight mixing. And you can set the convergence criteria for a force relaxation, which I'm going to show you in the next chapter. Here is the criterion for how much should two displacements between two iterations vary at most, and here how much should the forces be at most in a mean sense. And the last parameter you can set is the force converged, which tells the program how accurate you want to calculate your forces for each ground state calculation before you take it as a displacement and relaxation step. There are some additional tags for each atom species specifically. The first one is, do we want to calculate the forces for this species or not? And the second one is, which directions of this species can relax or cannot relax? So if you want to relax this atom only in the Z direction, you would write FFT right here. Okay, that's all on how we calculate forces and how we do it in FLEUR explicitly. And now I'm going to talk about what we can use this for. Most prominently, of course, we can use this to do structural relaxations. So we take an initial atomic configuration and we say, okay, this and this atom, they can move around and set direction. And we want to see, will they move around? Do we get an energetically more favorable ground state from this? For this, we first converge the system to its ground state, then calculate the forces with the switches I just showed you. And then we will displace the atoms accordingly. If you see the displacement is very, very small and the forces are very, very small, okay, we're converged. We can take the system as is. If not, we're going to converge the newly shifted system, then calculate the forces again, rinse and repeat until we have force and displacement convergent. And then we have, if everything went right, of course, an energetically more preferable state, which we can then work on with. For example, if we have such a relaxed state, we can then use this to construct phonons for this system. And this we can do by a finite displacement or frozen phonon approach. So we basically simulate a phonon by looking at the waveform of the phonon and displacing atoms over several unit cells accordingly. The supercells that we need for that are, for example, generated by the phonopi code. We can feed them our initial input for the perfect unit cell and get the supercells out. We then do ground state and force calculations for each of these supercells and feed the remaining information from the forces back into the phonopi code. You might know from your background in physics that phonons are related to the second derivative of the total energy by atomic displacements. And the second displacement is basically done numerically. So we have forces from shifted atoms. And if we divide this over how much we displace them, we get the numerical second derivative of the total energy by the atomic positions, which corresponds to the dynamical matrix. And from this dynamical matrix, we can calculate the phonon spectrum as its eigenfrequencies, basically. So those are two very neat uses for forces. And I have some additional information for you in this context. If you want to do relaxations with the FLEUR code, you should always reduce the muffin tin radii to about 95% of what they are generated to at default. So when you have atoms that move towards each other in the relaxation, they do not crash into each other as fast. This is just something you do for safety. And this whole relaxation workflow, which I showed you, which you normally would do by hand, each of the 3 steps repeatedly, is completely implemented as a workflow into the FLEUR AIDA plugin. So if you are fluent in working with AIDA, I suggest you use this plugin because it saves you a very large amount of work in rinse and repeat fashion. Here I now have some caveats on what we do not do considering derivatives of the total energy in FLEUR. We do not calculate the stress tensor in a similar fashion, so we do not do derivatives by the lattice parameters. If you want to do a lattice optimization in that context, you first need to do a Birch-Monaghan fit, so a minimization of the total energy by volume. And FLEUR is also not a code that should be used for molecular dynamics. So we do not use the relaxation over several steps of a system as a substitute for a evolution over time of a system. This is not what FLEUR is programmed for. This is not our concept. We are strictly a solid state code. This is not what is meant to be used for. And one thing I want to highlight personally is that the idea of energy derivatives reappears in the context of density functional perturbation theory, which can also be used, for example, to calculate phonon spectra. This is a feature currently in development and something that I actively work on as part of my PhD thesis. Okay, so this is how to calculate forces, why we calculate forces, and what we use them for. And now I want to show you just a very small test system as a proof of concept that our forces work. And this is going to be FCC aluminum. Quite boring, I know, but I just want to highlight the main features. We're going to take it as a simple cubic setup with a 4-atom basis. And we're going to displace the atom at the center of the system at 0, 0, 0 a little bit to the positive z direction. Then we're going to calculate the forces and do a relaxation run to see that it hopefully quickly relaxes back into the origin, which should very clearly be dictated by the symmetry of the other atoms. And if we look at the forces in the first iteration, we instantly see, okay, this is quite nice. We displace the atom into the positive direction, and then, of course, it wants to go back to the negative direction, which is, of course, also what it's going to do in the next relaxation step, because only this atom was allowed to move. And if we sum up the forces for all the 4 atoms, we see that the drift force for this particular example is very, very negligible. It's only 1/1,000,000th of the forces of each separate atom. So this is not a case where we need to think about force levels right now. And if we look at the relaxation behavior over the 4 relaxation steps that we need to go back to the perfectly symmetric 0, 0, 0 case, we see that the force is basically proportional by a negative constant to the displacement for this simple setup, which should not surprise you if you talk about small deviations from an equilibrium position. This should kind of reproduce spring system, so a linearly bound system. And you see that this relaxation works very, very fast and very, very accurately to 0. And so this works as it should. And this might kind of bore you right now, but the more interesting stuff will be done in the tutorial, where we're going to talk about a film system with a non-constructed z displacement, which we actually need to think about, and we actually want to know, okay, where will this z atom move? And not one where we initially already know where it should be. But that's for the tutorial. For now, I'm finished, and I wish you a very nice day, and I thank you for your time. See ya!